Introduction. Today we will learn differential equations. The question is, why do we need to learn differential equations? Can anyone tell? Teacher, because a differential equation is an expression that relates quantities and their rates of change. Very good. Anybody else? Teacher, can we represent the growth rate through differential equations? Yes. And the solution to a differential equation is not simply a number, but it is a function. Isn't it interesting? Let's start now. In this lesson, you'll learn how to solve the differential equations. Objectives. At the end of this lesson, you'll be able to find the order and degree of differential equations, find the general and particular solutions of differential equations, form the differential equation when general solution is given, solve differential equation by separation of variables method, solve homogeneous differential equations, solve linear differential equations. Basic concepts. An equation involving independent variables, dependent variables, and their derivatives or differentials is called a differential equation. A differential equation which involves only one independent variable is called an ordinary differential equation. For example, dy by dx minus x log x is equal to 0. Order of differential equation. The order of a differential equation is the highest derivative that appears in the differential equation. For example, 1 by x into d2y by dx square equals e raised to the power x is the differential equation. Order of highest order derivative, that is, of d2y by dx square is 2. Degree of differential equation. The degree of a differential equation is the power of the highest derivative term. For example, 1 by x into d2y by dx square equals e raised to the power x is the differential equation. It can be written in the form 1 by x into d2y by dx square whole power 1 equals e raised to the power x. Degree of highest order derivatives is 1. Example. Find the order and degree of differential equation. d2y by dx square whole power 3 plus dy by dx equals sin x. Solution. Given d2y by dx square whole power 3 plus dy by dx equals sin x. Order 2. Degree 3. General and particular solutions of a differential equation. General solutions. A general solution to an nth order differential equation is a solution in which the value of the constant c in the solution may vary. For example, in the differential equation, dy by dx equals e raised to the power x minus 2, name it as 1. The general solution can be found by integrate equation 1 on both sides. We get y equals e raised to the power x minus 2x plus c, name it as 2. The value of c in the solution could be any, because when we differentiate y, c becomes 0 as the derivative of the constant is 0. Particular solutions. A particular solution to an nth order differential equation is a solution in which there is a particular value for the constant c. These types of solutions occur in the initial value problems. The general solution to the differential equation dy by dx equals e raised to the power x minus 2 is y equals e raised to the power x minus 2x plus c when y0 equals 3. It means that at x is equal to 0, y equals 3. Put the values of x and y in equation 2. We get c equals 2. So the particular solution to the differential equation is y equals e raised to the power x minus 2x plus 2. Example. Find the particular solution of the differential equation dy by dx equals 4x minus 2 given y equals 5 when x equals 3. Solution. Given dy by dx equals 4x minus 2. dy equals 4x minus 2 dx. Integrate both sides. Integral of 1 with respect to y equals integral of 4x minus 2 with respect to dx. Y equals 2x square minus 2x plus c is the general solution. When y equals 5, x equals 3. 5 equals 2 into 3 square minus 2 into 3 plus c. By calculating we get c equals minus 7. The particular solution for the given initial conditions is y equals 2x square minus 2x minus 7. Formation of a differential equation whose general solution is given. To form a differential equation from a given equation in x, y, and containing arbitrary constants, the given equation is differentiated wrtx successively as many times as there are arbitrary constants. These equations are used to eliminate the arbitrary constants. The equation obtained by eliminating the arbitrary constants is the required differential equation. In general, if the equation between two variables contains n arbitrary constants, then the differential equation obtained by eliminating these arbitrary constants will be of order n. Important points. Equation of a line is y equals mx plus c, where m and c are arbitrary constants. Equation of a line passing through the origin is y equals mx, where m is arbitrary constant. Equation of the circle having center h, k and radius r is x minus h whole square plus y minus k whole square equals r square. Example. Find the differential equation of the family of curve. Y equals m cos 6x plus n sin 6x, where m, n are arbitrary constants. Solution. Given y equals m cos 6x plus n sin 6x, name it as equation 1. Differentiating equation 1 with respect to x, we get dy by dx equals minus 6m sin 6x plus 6n cos 6x. Name it as equation 2. Differentiating equation 2 with respect to x, we get d2y by dx square equals minus 36m cos 6x minus 36n sin 6x. It can be written as d2y by dx square equals minus 36 into m cos 6x plus n sin 6x. Mark it as 3. Put the value of y in equation 3, we get d2y by dx square equals minus 36y. Therefore, d2y by dx square plus 36y equals 0. This is the required differential equation. Methods of solving first order. First degree differential equations. Differential equations with variables separable. The differential equation of the form dy by dx equals fx by gy or gy by fx or fx into gy. They can be written as gy dy equals fx dx or dy by gy equals dx by fx or dy by gy equals fx dx respectively, and after that they get integrated. Example. Solve the differential equation. dy by dx equals e raised to the power x minus y plus x square into e raised to the power minus y. Solution. Given dy by dx equals e raised to the power x minus y plus x square into e raised to the power minus y. Taking common e power minus y from the right hand side, we get dy by dx equals e raised to the power x plus x square into e raised to the power minus y. Separate the variables and we get e raised to the power y dy equals e raised to the power x plus x squared dx. Integrate on both sides, we get integral of e raised to the power y with respect to y equals integral of e raised to the power x plus x square with respect to dx. That is, e raised to the power y equals e raised to the power x plus x cubed by 3 plus c. This is the required general solution of the given differential equation. Homogeneous differential equations. A first-order differential equation in the form mx, y dx plus nx, y dy equals 0 is said to be homogeneous if both coefficient functions m and n are homogeneous equations of the same degree. Method of solution. Use substitution y equals vx or x equals uy. The resulting equation after the substitution is separable equation. Example. Solve the differential equation. dy by dx equals x square y by x cube plus y cube. Solution. Given dy by dx equals x square y by x cube plus y cube. Name it as equation 1. This is a homogeneous differential equation. We will put y as Vx. Differentiating on both sides with respect to x, dy by dx equals x into dv by dx plus v. Therefore, equation 1 can be written as v plus x into dv by dx equals vx cube by x cube plus v cube x cube. V plus x into dv by dx equals v upon 1 plus v cube. X dv by dx equals v upon 1 plus v cube minus v equals v minus v raised to the power 4 upon 1 plus v cube. Integrate on both the sides, we get integral of 1 by x with respect to x equals minus of integral of 1 plus v cube by v raised to the power 4 with respect to dv. Log of mod x equals 1 by 3 v cube minus log of mod v plus log c. Log of mod of vx by c equals 1 by 3 v cube. It implies that Vx by c equals e raised to the power 1 by 3v cube. It implies that y by c equals e raised to the power x cube by 3y cube, or y equals c into e raised to the power x cube by 3y cube. Linear differential equations. The solution of the linear differential equation dy dx plus py is equal to q, where p and q are functions of x only, is y into integrating factor equals integral of q into integrating factor with respect to x plus c, where I dot f stands for integrating factor and it can be found by the formula given below. I dot f equals e raised to the power integral of p with respect to x. If the differential equation takes the form dx by dy plus px equals q, where p and q are functions of y and not of x or constants. In this case, the integrating factor is I dot f equals e raised to the power integral of p with respect to y, and the solution is x into integrating factor equals integral of q into integrating factor with respect to dy plus c. Note: if the coefficient of dy by dx is not unity, it must be made unity by dividing throughout. Solve the differential equation. Dy upon dx plus 3x square y equals 6x square. Solution. Given dy by dx plus 3x square y equals 6x square. Name it as 1. The given equation is linear with px equals 3x square and qx equals 6x square. Integrating factor can be found as I dot f equals e raised to the power integral of 3x square with respect to dx equals e raised to the power x cube. Multiply equation 1 by integrating factor, we get e raised to the power x cube into dy by dx plus 3x square into e raised to the power x cube into y equals 6x square into e raised to the power x cube, or d by dx of e raised to the power x cube into y equals 6x square into e raised to the power x cube. Integrating both sides, we have e raised to the power x cube into y equals integral of 6x square into e raised to the power x cube with respect to dx equals 2 into e raised to the power x cube plus c. Solving for y, we get y equals 2 plus c into e raised to the power minus x cube. Did you know? Gottfried Wilhelm Leibniz gave the method of variable separation. He also provides the solution of linear differential equation. Summary. Let us summarize what we have learned. An equation involving independent variables, dependent variables, and their derivatives or differentials is called a differential equation. The order of a differential equation is the highest derivative that appears in the differential equation. The degree of a differential equation is the power of the highest derivative term. A general solution to an nth order differential equation is a solution in which the value of the constant c in the solution may vary. A particular solution to an nth order differential equation is a solution in which there is a particular value for the constant c. If the equation between two variables contains n arbitrary constants, then the differential equation obtained by eliminating these arbitrary constants will be of order n. In differential equations with variables separable, we first separate the variables and then integrate them. A first-order differential equation in the form mx, y dx plus nx, y dy is equal to 0 is said to be homogeneous if both coefficient functions m and n are homogeneous equations of the same degree. First, we substitute y equals vx, and then the resulting equation is variable separable. The solution of the linear differential equation dy by dx plus py equals q is y into integrating factor equals integral of q into integrating factor with respect to dx plus c, where I dot f stands for the integrating factor I dot f equals e raised to the power integral of p with respect to dx, where p and q are functions of x. If the differential equation takes the form dx by dy plus px equals q, then its solution is x into integrating factor equals integral of q into integrating factor with respect to dy plus c, where I dot f equals e raised to the power integral of p with respect to dy, where p and q are functions of y and not of x or constants.